BKW Physics. I'm Mr. McConnelly, and we're going to continue our talk on momentum and impulse by talking about the conservation of momentum today. The way I want to start out is, first of all, encourage you to watch collisions in space. And there's on YouTube, there's a YouTube video, and you can look at someone in the International Space Station who is colliding things in outer space so there's no friction involved, and it really gets you the idea more clearly of what's going on. But I have a demonstration here which works well here on Earth, and basically what it is, it's called a Newton's cradle. But as I pull two of the balls back, let's say, and when I pull them back, you can see that that energy, or that momentum that we're talking about, is imparted to the stationary balls that are on the other side still. And what's really interesting is the ball in the middle really doesn't go anywhere. And then I can do it with one ball, which is really cool because you can see that that momentum is being passed through three of the balls in the middle. You can do things like pull the two outside ones, which is always neat, as long as it continues to line up. And my alignment on this is not perfect, but it works good. That. Now this is where it gets weird, I think. That's when you think about it. Well, if I pull three back, what's going to happen now? So watch this. Watch that again. It's almost hard to grasp what's going on when you first see it. See that? So you got three, and it comes down and it hits, and then it takes three to the other side, and then it hits and it takes three to the other side. So all of these things show, is a Newton's third law demonstration, and it shows Newton's third law, which is force equal opposite force, but it also shows the conservation of momentum pretty clearly. Is there any other scenario you want to try before I move this to the side? 4 to 1. So if I pull 4 back, which is always dicey because sorry to keep it like that, I'm going to pull back that. Isn't that weird? It's really cool. It actually takes the 4 and transfers it to 4 over here. So what we're saying here with the conservation of momentum is basically this. Whatever momentum you had when the scenario started, so when the scenario started, like if I pull 2 back again, and these are swinging down, that's the scenario starting, there's a certain amount of mass, there's a certain amount of velocity, mass times velocity, you get the momentum. Well, what do these have down here? Well, since they have a velocity of 0, how much momentum do they have? 0, because anything times 0 is 0. Now, when the two that come down that actually have momentum, when they hit, this momentum is going to be imparted to the two over here. How much momentum will they have? The same as the two that were being dropped in the beginning. And how much will the 3 have that are left behind? 0. So what you say in conservation of momentum is that if the total momentum, to put a number to it, is 20, and these are swinging down, then after the collision happens and these two swing away, these are going to have 20. And the law of conservation of momentum says the total momentum remains the same. So if we can swing to the board now, we got a few notes that we can jot down on this. We can do an example. You can slide that up, even if it stutters. So what I've written on the board is conservation of momentum. I kind of just summarized what I was just saying. The total momentum of a closed, isolated system. That means in our scenario of the example, we have these 5 steel balls, and there's nothing outside that's interfering with them. The 5 steel balls interact. That's the closed, isolated system. The closed, isolated system, total momentum does not change. It's an application of Newton's third law, but don't confuse the two. Newton's third law is force, and conservation of momentum is momentum. Two different things, but it's kind of two tied together. So, in terms of a picture, we could draw something like this, just to help you remember what's going on. If I have A and B, 2 spheres, head towards each other, and each of them in this case are moving. Let's even say that each of them have the same mass in this case. It makes it kind of easier for the first example. So let's say the momentum of this one is 10, and the momentum of this one is 10. And what are the units for momentum again? Kilogram meter per second, because it's mass times velocity. Kilogram meter per second. Well, you know that they're going to collide eventually in the middle here. Clack, clack. That's the universal symbol for they're hitting each other. And at that moment right there, it seems as though the momentum is lost, gone. Because for a moment they stop. There's an instant when they seem to stop. Because remember, kind of think of these as positives and negatives. This one we'll say is negative because it's going left, and this one is positive. So when they meet in the middle, you really got nothing per se. But then afterwards, what's going to happen is that A is going to drift off this way, and B is going to drift off this way, and the momentum is going to be 10, 10 again. And this shows through this process, 1, 2, 3, this is the conservation of momentum. Now, what about if they stick together? Now, in this case, if they stuck together, doesn't that violate the law of conservation of momentum? I mean, you had 10 and 10, and then you got. So this is one case when they bounce off. What about if they stick? Seems as though we're violating some sort of physics law here. But we're not. Because take my positives and negatives again. What does this add up to? What's the total here? 0. What's the total here? 0. So if they are to stick together, basically you just go step 1, step 2. There is no step 3 if they stick together, because that's it. They cancel, they're done. Get it? And you can, this could be true too even if the masses are different. So say you got A and B, and I'm kind of drawing a little different size so you can see that they're different. And this one has a momentum of 10, and this one has a momentum of 20. Now when they clack in the middle, what do you got left? I got 10 left because you can see that there's not a big cancellation if this is negative and this is positive. You've got 10 left, and it's going to be in the negative direction. So this, as a whole, is going to continue to drift to the left after they hit each other. And this is kind of how it works when you're playing pool. If you understand the laws of momentum and some angles, you can be really good at the game of pool. Because it's all about that. So how do we write this as like a physics equation? Because it always comes down to that. Well, this is how it works. You say the momentum before, and that means before the collision, is equal to the momentum after the collision. So there's always two objects you're dealing with here. So you go, the next step is you say the momentum of the A object, or it could be object number 1. I don't really care what you use. This is just for example. The momentum of the A object plus the momentum of the B object beforehand is going to be equal to the momentum of the A object plus the momentum of the B object afterwards. And the way you denote after is by the little up there. Okay? Now, if we apply this to a real situation, we can solve something. So, in our textbook, there's an example, and I'll just kind of talk my way through it. There's an example where there's a goalie who's playing ice hockey, and he's a 75-kilogram goalie. All right, I'm going to jot down some info. The goalie is 75 kilograms. And he's the goalie, so he's just standing there at the goal. If you're familiar with hockey, they usually don't move too terribly much. So the goalie has a velocity, this is his mass, and he has a velocity of 0 at the beginning of the situation. Now, the puck has a mass of 0.105 kilograms, and the puck is moving quite rapidly at 48 meters per second when the scenario starts. So basically, you have a goalie guy standing here. He's standing in the goal. He's going to try to stop the puck, and the puck is whipping through the air, coming right at him super fast. But goalies, especially hockey goalies, have pretty quick reaction time. So he's able to actually catch this puck. But let's say that he catches the puck, but he has his ice skates lined up in such a way, like he's not bracing himself very well. He's got his feet like pointing front to back like this. So he catches a puck going 48 meters per second. What's it going to do to him? It's going to like push him back a little bit. You know, it's like if someone throws a basketball at you and you're not really bracing yourself, it's like kind of like knocks you back a little bit. So the puck is actually going to knock him back. And I want to know, how fast is he going to drift backwards? Let's assume there's absolutely no friction on the skates. It's a perfectly frictionless environment, because that makes the problem easy and doable. So let's go back to this. So we know this is what's before, this is what's after, there's two objects. What do you want to be what? I think I'm going to call the goalie A. Okay? Here's the goalie, he's going to be A. And the puck's going to be B. Is that okay with you guys? So, beforehand, the mass A, which would be the goalie, times the velocity A, so I'm taking this and I'm breaking it down a little bit further, plus the mass B, velocity B, is going to equal mass A, velocity A afterwards, plus mass B, velocity B afterwards. See, I just broke those each of those momentums equal into mass and velocity. Now, which ones are zeros? Well, definitely the goalie beforehand, he wasn't moving, he's a zero. I'm just going to get rid of that right now. This one definitely had some numbers associated with it. So the mass was 0.015, velocity was 48. Okay, so I got some numbers in there now. Now over on the, I'm going to let that phone ring. Over on the right-hand side here, what do we got going on here? Well, we got the mass of the goalie, which is 75. We got the velocity afterwards, but we don't know that yet, right? And then we got the mass of the puck, and we got the velocity of the puck afterwards. But we don't know what that is either. So, what do you know about these two velocities, though? Why are they the same, Chris?
Because they're now both combined under one
They're both
person.
combined because the goalie caught the puck and now they're both drifting backwards together. So whatever their speed is, I don't really need to call them A and B anymore. They're just afterwards velocity. Okay? They're the same number. So now we got to do a little math, because if you got a common term in two different spots, you know how you can pull it out? So we can do 75 kilograms. Can you answer that, someone? Nice. Plus 0.105 kilograms. And we're going to pull out the velocity prime. We're going to leave everything on the left-hand side the same. And when we actually solve for the velocity prime, we're going to get that the goalie is drifting back at 0.06 meters per second, which is almost negligible. He probably wouldn't even really move, because in real life there would be some friction between the ice and the skates. But in this scenario, if there's no friction, he's going to slowly shoot back after he catches the puck. That's one example of how you can use momentum for these type of problems. Physics.